We're going to start talking today about step functions. So let's just play around with step functions. Our basic definition is that the step function u sub c of t, and we've seen this once before, u sub c of t is 0 if t is less than c, and 1 if t is greater than or equal to c. So I'll just draw a quick picture here. Here's our t-axis, and we'll draw y equals u sub c of t. It's 0 until we get to c. But then at c it becomes 1. So this is at height 1. Now, let's start looking at some examples of step functions. Let's begin with this one. I'll draw just a picture here, and we'll talk about how we can represent this different, more complicated step function in terms of our standard step functions. So I want to look at a function which is 0 until you get to 2, and then between 2 and 3 it should be 2. So just like before, I'll say the graph looks like this: 0 there, 2 there, until we get to 3. And at 3 it becomes minus 1. And then at 4 it becomes 0 again, and is 0 after that. So we have a step function which is 0 everywhere except between 2 and 3 where it's 2, and between 3 and 4 where it's 1. I'll call this one k of t. Here's a question. How can we rewrite k of t in terms of a standard step function? Well, let's start with the fact that k is 0 up until 2. Now, at 2, k is 2. So if I start with 2 times u sub 2 of t, then that would be a function which is 0 until 2, and then is exactly 2 because I've doubled u sub 2 everywhere after that. But of course, that's correct between 2 and 3, but then that's wrong after 3. So I have to change it, but my change only will begin after t equals 3. Well, what happens at t equals 3? We want to drop 3 units. So to drop 3 units when t equals 3, I'll subtract 3 times u sub 3 of t. And then what happens? Well, that will not change anything that happens with k of t between 0 and 3. But after 3, it will drop everything 3 units. So instead of being 2 up here, it would be down here at negative 1. But it would stay at negative 1 forever after that. Well, so I want to change it back to 0 at 4. So what I want to do is add something which moves me up 1 unit beginning at 4. So that's easy. I just add u sub 4 of t, like this. So now I'm done, because now we see that this function is 0 until we get to 2, because all 3 of these are 0. Between 2 and 3, these last 2 terms are 0, and u sub 2 is 1, so k is 2 between 2 and 3. Between 3 and 4, this last term, u sub 4, let me be clear about that, u sub 4 of t is 0. So between 3 and 4, I just have 2 minus 3 is negative 1. And then after 4, all these terms are 0, and k is back to 0 again. It should be pretty clear that you can represent any step function in this manner. Remember, step function is just a function that takes a finite number of values, each one of which on some interval. And we can create a simple formula for such a function using linear combinations of standard step functions. Let's see one more example just to practice this. I'm going to draw one more picture here. Let's say we want a function which now starts at 1 until we get to t equals 1. So this is our t-axis here. This is 1 on our y-axis. And then I want it to be up to 2 beginning at 1 and going all the way out to 3. So say here's 3. And then beginning at 3, I want it to be down at -1 again, just until 4. And then after 4, I want it to be back to 1. And then stay at 1. So how can we create a function that behaves like this? Well, notice here, everything in these examples is with t greater than or equal to 0. So we can create, I'll call this f of t. I'll call this f of t and write it in terms of the step functions. We start with 1, and that would be correct until t equals 1. Then beginning at t equals 1, I want to add a single unit. So I want to add u sub 1 of t. That bumps me up 1, beginning when t equals 1, and then I'll be at a level 2 here. Then I want to drop 3 units, beginning at 3, which we do by subtracting 3 u sub 3. Then I want to rise up by 2 more units, beginning at t equals 4. So f of t can be written in this manner. We start with the constant 1, and then we just have these other step functions. And of course, you can think of 1 if you want as u sub 0 of t. That's 1 beginning at 0. Now, once we see that we can write any step function in terms of these standard step functions, we realize it would be a good idea to be able to find the Laplace transform of these standard functions. Then, by linearity, we'll be able to find the Laplace transform of any step function. So, how do we do that? Well, here's a very simple theorem. It says the Laplace transform of the standard step function u sub c of t. It's not just a theorem, I have the whole computation here. We just compute that by taking an integral from 0 to infinity of e to the minus st times u sub c of t. Well, u sub c of t is 0 until you get to c, and then 1 afterwards, so that's the same as an integral just beginning at c instead of beginning at 0. Remember, for all of these, and I should have mentioned for u sub c of t, we're going to be insisting that c is greater than or equal to 0 here. So this will be an integral from c to infinity of e to the minus st dt. And you can just compute this. I didn't write this down before. You can just compute this very quickly. That's the limit as a goes to infinity of the integral from c to a of e to the minus st dt. That's the limit as a goes to infinity of minus 1 over s e to the minus st from c to a now. That's the limit as a goes to infinity. Let me just fix this. Of 1 over s, or minus 1 over s e to the minus sa, plus 1 over s e to the minus sc. And of course, this part tends to 0. As limit 0, so we just end up with e to the minus sc over s, and all of this is when s is greater than 0, because of course it's for s greater than 0 that this has limit 0. So the Laplace transform of a basic step function, u sub c of t, is just e to the minus cs over s. Notice that the special case is here that at u sub 0 of t, which is our standard function 1, this is when t is greater than or equal to 0, we know the Laplace transform of 1 is just 1 over s, which is exactly what we get in this formula when c equals 0. How would we take the Laplace transform of this function k of t that we had earlier? So let's take a quick look back. This function k of t was 2 u sub 2 minus 3 u sub 3 plus u sub 4. Well, the Laplace transform of k by linearity would just be twice the Laplace transform of u sub 2 of t minus 3 times the Laplace transform of u sub 3 of t plus the Laplace transform of u sub 4 of t. And by this simple formula, this is just 2 e to the minus 2s over s minus 3 e to the minus 3s over s. Then we have plus e to the minus 4s over s, which you can easily simplify, so I won't bother doing it here. So computing Laplace transforms of any step function really becomes a rather simple matter once you know the Laplace transform of the basic standard step functions.